Let me introduce today's speaker. So we have David Pechersky from University of Toronto, who's going to talk about orthodiagonal maps, tiling of rectangles, and their convergence to the Riemann map. So, David, the stage is yours.
Sure, thank you. So thanks a lot to the organizers for the invitation. So the story I'm going to tell is something like this. So I'm going to start with a brief overview of complex analysis, discrete complex analysis. I'll talk about these tilings of rectangles that'll feature in this talk. I'll talk about their connection to conformal maps. Sort of heuristically, the intuition is that these tilings are going to be some sort of discretization of a conformal map. And then we'll get to our main result, which is this proof that, okay, we can actually show that this heuristic is kind of true by proving that these things do in fact converge to a limiting conformal map. So, okay, so discrete complex analysis. So as mentioned in the talk abstract, this is the study of discrete holomorphic functions. These are functions on a graph embedded in the plane that satisfy some discrete version of the Cauchy-Riemann equations. And of course, there are many choices for your embedding, and there are various ways to discretize the Cauchy-Riemann equations. So the focus is very much on sort of choices of graph embeddings and choices of the discrete Cauchy-Riemann equations on these embeddings that sort of lead to nice properties. In particular, we'd like our, whatever we call a discrete holomorphic function, we'd like it to have a lot of the properties that we see from continuous holomorphic functions in the plane. So for instance, as an absolute minimum, wrong thing. Cool. So as an absolute minimum, we'd like discrete Morera. So we want it, when we integrate over closed contours, we want that to be 0. We have some notion of what it means to be discrete harmonic on a weighted graph. And so we'd like our discrete holomorphic functions, the real and imaginary parts should be discrete harmonic. And we also expect some sort of a priori regularity estimate. So the story is that in the continuum, if you satisfy the Cauchy-Riemann equations, your function is not just complex differentiable, it's smooth. And in fact, it's analytic. And so I don't know what a smooth or an analytic function is on a graph, but you should have, at least you should have some sort of similar story with your sort of discrete complex analysis. So maybe, okay, I don't know what a smooth or an analytic function is on a graph, but you might expect that, okay, you have like Hurler, if you satisfy discrete Cauchy-Riemann, you're already like Hurler regular, or you have Lipschitz regularity, something like that. Right. So just some highlight reels. So the subject of discrete complex analysis, this stuff is classical, and it goes back to these papers from the 40s and 50s, but there's been a lot of interest in this stuff very recently, in probably the past 20 to 30 years, because of this connection with 2D statistical physics at criticality. So in particular, there's like the work of Smirnov, which leveraged these techniques to show prove Carty's formula for critical percolation, the convergence of critical percolation interfaces to SLE6, the convergence of interfaces in the critical Ising model to SLE3, conformal invariance for fluctuations in the dimer model. This was done by Kenyon in the 90s, though it's since been extended to a more general setting. And just as a remark, so this is a recurring protagonist sort of in this business. So Schramm-Lochner evolution, or SLE kappa, it's this one parameter family of random curves parameterized by kappa greater than 0. that is characterized by conformal invariance and this Markov type property called the domain Markov property. So the thing to just keep in mind is that these are some family of random curves, and because they're sort of the unique random curves that satisfy certain properties, they appear as the interfaces in critical statistical physics at 2D, in 2D, right? So all of these proofs, they roughly go something like this. So you start off with critical statistical physics model defined on lattice. So the example maybe to keep in mind is the Ising model. It's very easy to sort of define what the Ising model is on a microscopic level in terms of, you have this guy at each vertex, you can be spin up and spin down, and you kind of want to be aligned with the spins of your neighbors, but then there are also some thermal fluctuations thrown in, right? And so it's very easy to sort of, what you're interested in is you want to extract from the microscopic description the macroscopic behavior of this model. So what happens when I zoom out? So for instance, like you have the Ising model, critical Ising, say, and you zoom out and you're interested, what do the interfaces between the +1 and -1 regions look like, right? So you'd like to answer these like big picture questions that come out of these microscopic description of your model. And the sort of the discrete complex analysis way to approach these questions is, okay, first you identify some discrete holomorphic observable in the model. These a priori regularity estimates that I talked about earlier, they tell us that these observables, as our lattice mesh shrinks to 0, oh right, and maybe I should have mentioned that, okay, getting the big picture out of these lattice level interactions, the way you sort of prove that rigorously is you ask yourself, okay, I let the mesh of my lattice shrink to 0, what happens, right? So this is what we're always doing in this business. And so we have these discrete holomorphic observables, and as our lattice mesh shrinks to 0, these guys are pre-compact with respect to the topology of uniform convergence on compacts. So this tells us we have subsequential limits. And then since we have the discrete holomorphicity of the observables, this gives us holomorphicity of any subsequential limit. And so since the limiting observable is holomorphic, we can identify it by its boundary behavior. And so, since all of your subsequential limits have to be the same, it turns out you converge to you have to converge to the relevant continuum limit. And then from there, the convergence of this observable is leveraged to prove convergence of the discrete random objects of interest. So once you have a handle on the convergence of this particular functional of your model, you can sort of bootstrap this to get convergence of, I don't know, say like your interfaces to like SLE6, SLE3, etc. So this is sort of what's going on here. And so let me just introduce, so what is sort of the notion of discrete complex analysis that I'm going to be talking about in this talk. So an orthodiagonal map, this is a finite connected planar graph, along with an embedding in the plane so that each edge is a straight line segment, each interface is a quadrilateral with orthogonal diagonals, and the boundary of the outer face is just a simple closed curve. So I have a picture of one of these guys right here, right? And the thing to just keep in mind is that any quadrangulation with boundary is bipartite. And so we always have this natural bipartition of the vertices into the primal vertices, sort of, which we color black, and the dual vertices over here, which we color white.
So I just have a very quick question. So in this example, we see that the quadrilaterals are not necessarily convex.
Yes.
Okay.
So that's a good point. So in general, you can kind of, sorry, I don't know why that glitched. But in general, yeah, so they don't have to be convex as long as this line over here is, intersects with a 90-degree angle to this line, it's okay. So they don't have to be convex. The two diagonals don't actually have to intersect, but if you extend them, they do have to meet at 90-degree angles.
Okay.
So
Thanks.
thank you. That is actually a good observation. Cool. So now from this picture, given an orthodiagonal map, we have this associated primal graph, which is basically, I just join two of these black vertices if they share a face in my original graph. And similarly, I have the dual graph, which is I join any two white vertices that share an edge in the original graph, right? And maybe this is, I imagine most people here have already seen this, but in the event you haven't, so this seems kind of restrictive, right? We can only talk about, we're interested in talking about discrete complex analysis on embedded graphs, and we're already somehow restricting our attention to quadrangulations with boundary for the underlying graph, right? But of course, in the event that you haven't seen this, well, we have this nice bijection, which between, say, quadrangulations with n faces and planar maps with n edges, just purely on a graph level, there's nothing orthodiagonal going on here. And the bijection is, of course, as follows. So here I've drawn down some planar map. And what I do is, okay, I form the dual by putting a vertex inside each face and then joining two faces if they share an edge. And then from there, what I do is, if my primal edge, if I have two vertices and they have corresponding primal and dual edges that crossed, so one black guy and a white guy, then I join these guys with a red edge in this picture. And then in the next step, I just erase all my original primal and dual edges, and I'm left with a quadrangulation, right? So you can just check that this procedure gives you a guy with where each of these faces has four sides, and there are n faces because if you think about it, every face corresponded to an edge of your original graph. Right? So what the moral of this story is effectively is, okay, we're restricting our attention to quadrangulations, but not really. So the way to think of an orthodiagonal map is not as an embedded quadrangulation. It's, I took a graph and its dual, effectively, and I embedded them in the plane in such a way that the primal and the dual edges are orthogonal to each other. So that's sort of the intuition to keep in mind here. Okay, and the primal and the dual graphs, they come with weights on the edges. So the weights are defined as follows. So the weight on the primal guy is the weight of the length of the dual edge over the length of the primal edge, and then the weight on the dual guy is the length of the primal edge over the length of the dual edge. And notice that these two guys multiply to 1, right? And so just, maybe if you haven't seen this before, this seems a little bit strange. But so if we use this choice of edge weights, then simple random walk on both the primal graph and the dual graph is a martingale. And as a Markov chain, your simple random walk is reversible. So just as a reminder, a simple random walk on this, on our graph is just, with these edge weights, it's basically, if you're at the vertex X, the likelihood of going to the vertex Y is just proportional to the weight of the edge between X and Y, right? That's all this is saying. And I guess just one definition in case you haven't seen this before. So a discrete harmonic function, or rather, okay, a function, say, on the primal vertices is said to be discrete harmonic at X if the following is true. So this is, in case you haven't seen this before, this is the discrete Laplacian. on this graph. And you can rewrite this equation that the discrete Laplacian is equal to 0 as follows. So this guy just says that the value at h is some weighted average of the values at its neighbors. And so, this is reminiscent of the mean value property for harmonic functions. So it this should maybe convince you that this is the correct way to sort of discretize the Laplacian on just some weighted graph, right? Okay, so now we have our definition. So we say that a function, which is defined on the vertices of our original graph, so both the primal and the dual guys, we say it's discrete holomorphic if this discrete derivative across this edge matches up with this sort of discrete derivative across the corresponding dual edge. And if we use this as our definition of discrete holomorphicity, we get all the nice properties I suggested that we should have earlier. So you can check that f integrates to 0 over any closed curve in G. The real part and the imaginary part are all discrete harmonic functions on the primal or dual graph, depending on where you restrict. And we also have these a priori regularity estimates. So there's a bit of a history to this. So in 2019, in this nice paper, Jerison, Gurel, Gurevich, and Nachmias, they showed that you have this uniform modulus of continuity in the bulk for discrete harmonic functions on OD maps in terms of discrete Dirichlet energy. So it's not something particularly nice, but they managed to prove that, okay, if your Dirichlet energy is finite, then there's some modulus of continuity for discrete harmonic and discrete holomorphic functions. So it's not explicitly stated in this paper, but this was improved on by Chelcock, Losley, and Ruskik, where they showed that bounded discrete holomorphic functions on T embeddings where the corresponding origami map is better than 1 Lipschitz on large scales. Whatever that means. I could talk about what that means later, but effectively they're dealing with sort of a much more general setting for discrete complex analysis, of which orthodiagonal maps are a specific case. And they managed to show that so-called bounded T holomorphic functions, they're Hurlder in the bulk. And so in particular, the same result is true for OD maps. And then, of course, the thing I alluded to is, of course, the right sort of analog of the a priori regularity that we see in the continuum, the right analog, it should be Lipschitz regularity. So you have this intuition that, okay, harmonic functions are, bounded harmonic functions are Lipschitz in the bulk. So the same thing should be true on these orthodiagonal maps, since they're sort of good approximations of continuous 2D space. But proving this is still an open question. So I think there's some partial results in this paper where you make some additional mild regularity assumptions and you can get it. Regularity assumptions on your lattice, but in general, this is open. Okay, so just some comments. So firstly, all the standard lattices on which you do physics are orthodiagonal, right? So if I look at the square grid, it has this property that primal and dual edges intersect at 90-degree angle. Same story if we had the hexagonal lattice, right? Or the triangular lattice, which is dual. And in particular, if you've seen some of these like physics papers or some of these math papers, so isoradial graphs or rhombic lattices, which have been studied pretty extensively, these are precisely OD maps where all the interfaces are rhombi, right? So we're dealing with the strict generalization of that. And in particular, there's this double circle packing theorem, which tells you that if you have any 3-connected planar graph, this admits an orthodiagonal embedding. So there's actually quite a large class of graphs that you can embed in this way and do discrete complex analysis on. And as I alluded to earlier, there's sort of this more general setting that was introduced by Shelcock, Losley, and Ruskik, and Kenyon, Lamb, Ramasamy, and Ruskik, which are some sort of more general notion of discrete complex analysis. And in particular, like I said, in this Shelcock, Losley, Ruskik paper, they prove all sorts of nice sort of like regularity estimates for discrete harmonic and discrete holomorphic functions. Okay, so motivation. So we already have a lot of these results for if you restrict to simpler lattices like the hexagonal lattice or the square lattice. So why do we want to push? So the story is effectively that I think statistical physics on isoradial graphs at this point is sort of well understood. And so the question is, so why do we want to push things to this orthodiagonal setting, right? So one is universality, of course, right? So the easiest example of this is just a bell curve. So if you have something and it's, you have something object of interest, like maybe, I don't know, it's like the height of people, and there are a bunch of, it's influenced by a bunch of tiny independent random factors, the distribution of the fluctuations around the mean, it looks like a bell curve. And in particular, the central limit theorem tells us, okay, the distribution of these fluctuations doesn't actually matter. As long as they're small and they're independent, you still get this bell curve. And so we have a similar story in statistical physics where there's this intuition that the phenomenon we see is universal. And so in some sense, it shouldn't matter how we discretize our space. So if we define our model on a square lattice or a hexagonal lattice or a triangular lattice, it shouldn't really matter once we zoom out. The macroscopic picture that we get out of these microscopic interactions, it should be the same, right? And so, of course, one way of sort of rigorously proving a result like this is to say, okay, you take a general orthodiagonal map, or you take a general isoradial lattice, and you take the mesh to 0, you get the same behavior. So one is proving these universality results, and another is sort of applications to random geometry. So this is sort of one of the big, I think, problems in sort of modern probability theory. So the story is roughly the following, which is, okay, you sample a large planar graph uniformly at random in some sort of sensible way. So maybe you pick a triangulation with n faces uniformly at random, and n is large. And then you decorate this graph with a critical statistical physics model. So I stack an Ising model on top of this graph. And now the probability that I see a particular graph, it's not uniform. It's in fact proportional to the partition function of the Ising model on this graph, right? And if we think of our random graph as some random compact metric space, under appropriate rescaling, this thing should converge in distribution as we take larger and larger graphs with respect to this Gromov-Hausdorff distance to some limiting object. And the intuition we get from physicists is that, okay, this limiting object should be gamma Liouville quantum gravity for some parameter gamma. So in particular, your LQG metric is, you get it by integrating e to the gamma h along curves, and then you have this LQG area measure, which you get by integrating e to the gamma h over regions in the plane. And what is h here? H is the Gaussian free field, right? I'll just say that. So this is the Gaussian free field. And the problem here, of course, is that the Gaussian free field is this random distribution. It's not a function. It's very close to being a function, but it's not a function. And now we're doing this highly nonlinear thing to it, which is we're exponentiating. So this doesn't make sense. And this really doesn't make sense. And so, okay, as you might guess, there is some way to, a priori, what I wrote down is kind of nonsense, but there's a way of making sense of it where it's like, well, I regularize my GFF by convolving it with some smooth mollifier. I throw in some normalizing factor, I take a limit, and I can make sense of what these things mean. But then there's still this difficulty that, okay, we need to somehow relate this, limit under Gromov-Hausdorff limit on distribution with respect to Gromov-Hausdorff distance from step 3 to this object in step 4, which is effectively some random metric measure space, which I've defined it effectively as a random metric and a random measure in either the plane or the Riemann sphere. So in order to relate the object I got in step 3 to this guy in step 4, the natural thing to do is I want to take my random graphs and I want to embed them either in the plane or Riemann sphere. And so the first rigorous results to this effect are pretty recent. This is by Holden and Son for Cardy embeddings of random triangulations. And the thing is that, so discrete complex analysis was very useful for critical statistical physics just in the plane. And so what you'd like to do is you'd like to apply some of these same techniques to these embedded random graphs. And so in order to apply these techniques to these embedded random graphs, you need some sort of notion of discrete complex analysis that works here, right? And so in particular, so we have this Kirby-Andreev-Thurston theorem, which says any triangulation has a unique representation as the tangency graph of a circle packing up to Mobius transformations and reflections. And so if we look at this picture just by elementary geometry, if I have these two triangles, I can fit the dual vertex corresponding to this space. I can put it at the center of the incircles corresponding to these triangles. And then when I form the dual edge, it's just a fact from elementary geometry that these two guys will intersect at a right angle. Right. So a circle packing embedding will always give you an orthodiagonal map in this way. And so in particular, okay, this only really works for triangulations, but that's already pretty good. So in principle, at least, if you have a good handle on how to do discrete complex analysis on orthodiagonal maps, this should be sufficient to say something about critical statistical physics on random triangulations. Okay. So with that in mind, what we're going to do in this talk is we're going to use these discrete complex analysis techniques now to solve this sort of purely deterministic problem. So there's our story begins with these 4 undergraduates at Cambridge in 1940, Brooks, Smith, Stone, and Todd, who made this nice observation that if you have a planar graph and it has some edge weights and some distinguished source and sink vertices, in this case, let's say A is maybe this guy is our source, and maybe Z is our sink, then there's a correspondence of these guys with tilings of rectangles. So what is this correspondence? Well, what I do is the following. So I throw in a bunch of dual vertices. So this is what I form as sort of almost the graph dual, except I took the vertex corresponding to the outer face and I split it in 2, depending on sort of whether it came out of the left side or the right side, right? So I took the dual vertex corresponding to the outer face and it got split into these 2 new vertices, which I call A star and Z star, right? And then what I do is that I hook up a battery to each of these guys. So here I hook up a 1-volt battery, and here I hook up a energy of H tilde volt battery, where this is just some number, but I'll explain what it is later. And what I do is I set up, we want to solve for the voltage at each vertex. So since this is a 1-volt battery, the voltage drop between A and Z is 1 volt. And so as a convention, we can say, okay, the voltage is at A is 0, the voltage at Z is 1, and then we solve for the voltage at the rest of the vertices by solving a certain discrete boundary value problem on this graph, right? So this is the discrete boundary value for your primal guy, and then there's this corresponding boundary value problem for your dual guy, where the boundary condition on your dual guy is just the discrete Dirichlet energy of the solution to your first guy. So, of course, this is kind of weird, where we're taking the Dirichlet energy of our solution to one boundary value problem, and we're plugging it in as a boundary value for the second guy. But effectively, sort of what's going on is realistically, I won't talk about this much further, but really, we could have just said H tilde is given by this boundary value problem, and then H is the discrete harmonic conjugate of H tilde, whatever this means. And so our tiling map, we're going to define it on the level of the sort of quadrilaterals corresponding to this primal and dual graph. And it maps this quadrilateral over here to the following guy, which is H of W1, H W2, H tilde V1, H tilde V2. And maybe just keep in mind that because of the maximum principle for discrete harmonic functions, right? So this is some square. This is some interval in 0, 1. And this is some interval, or sorry, this should be an interval in 0 to energy of H tilde. And this is some interval from H tilde to 1, right? And so, let's see. Oh, and just one other comment, which is that, okay, because H is the discrete harmonic conjugate of H tilde, the following is true. And so, in fact, if you look at the rectangles over here that correspond to a quadrilateral face in our sort of in the quadrangulation corresponding to our network, the ratio of the width to the height of this rectangle is actually given by the weights, our original weights on the edges. And so this is the picture, right? So we have these quadrilaterals corresponding to primal and dual faces, and they correspond to these rectangles. And it turns out that by defining the tiling map in this way, I get some sort of nice tiling of the rectangle. So this might seem kind of mysterious, right? Like, especially I take a boundary value problem. I take some second boundary value problem where part of it involves plugging in the Dirichlet energy of the first guy as one of my boundary conditions. And then I form these little rectangles out of it. And for some reason, these rectangles, they sort of line up perfectly and they tile a rectangle. So this is kind of mysterious. Like, what happened here? And one answer to this question is that the reason you get this nice tiling of a rectangle out of this procedure is that these H and H tilde, these are sort of, this is the the guy that's H on the dual. Effectively, what we're dealing with is this is the discretization of some sort of conformal map. So let me maybe talk about that next. So just a comment. So the Riemann mapping theorem tells me any two simply connected domains are conformally equivalent. And so if I have, say, here's a simply connected domain omega, just so that we don't have to worry about boundary behavior, let's suppose the boundary is analytic. And we have these 4 distinguished boundary points, A, B, C, D, right? And my Riemann map Okay, if I fix the rectangle over here on the right-hand side, I can always map. I can always find a conformal map that sends this guy to this guy. And in fact, my Riemann map is determined by 3 real parameters. So what I can do is I can insist that A gets mapped to this corner of the rectangle, B gets mapped to this corner of the rectangle, C gets mapped to this corner of the rectangle, and the image of D is fixed, right? Because we don't have any more parameters left. And then similarly, maybe we picked a longer rectangle, say we have length L2, then again, we can map A to phi 2 of A, B to phi 2 of B, C to phi 2 of C, and then the image of D is fixed, but now it's moved from this arc where it was over here to this arc, right? So hopefully you can convince yourself that, okay, by playing with L, there's a unique length L so that I can map the 4 distinguished boundary points of omega to the 4 corners of this rectangle in this way, right? And in particular, so what is L? If you're familiar with this stuff, L is precisely the extremal length between these 2 arcs, if you're a complex analyst. And it's defined in terms of as the solution to some variational problem, but I won't really get into that here. So, okay, so now let's look at the boundary conditions for these H and H tilde guys, right? So, okay, so let's take a look. So if we have this conformal map that sends this guy to this rectangle so that, A gets mapped to this corner, B is mapped to this corner, C gets mapped to this corner, D gets mapped to this corner, well, let's see. So what happens along this boundary arc? This boundary arc gets sent over here, where its real part is constant. It's just 0. And so if we split our map phi into its real and imaginary parts, the real part is just 0 here. And similarly, if we look along this arc gets mapped over here, and the real part here is just L. And so our real part is just L over here. And similarly, we have these Dirichlet boundary conditions for H tilde. And now what about the rest of the boundary? Well, let's take a look at this arc, right? So CD got mapped over here, and the real part is constant. So if we take the derivative of the real part tangent to the curve, this should be 0, right? But then by the Cauchy-Riemann equations, the derivative of the real part tangent to the curve is precisely the normal derivative of the imaginary part. So we get that the normal derivative of H tilde is 0 here, and by the same reasoning, it's 0 here, and the normal derivative of H is 0 here, and the normal derivative of H is 0 here. And so we have this boundary. So it turns out that H and H tilde, which are the real and imaginary parts of this conformal map, they satisfy this boundary value problem. And even a little bit more than that. So let's take a look at this map. It sends this guy to a rectangle of length L. So the area of 5 omega is just L. And we can rewrite it like this. And by Cauchy-Riemann, this is precisely the Dirichlet energy of H tilde. So this should be very familiar. So in other words, this L guy, this is just the Dirichlet energy of H tilde. I guess backtrack. This is also Dirichlet energy of H tilde. So hopefully you kind of see the analogy. So we have effectively the real and imaginary parts of this conformal map. They come from the same boundary value problem as this network tiling business. Now, the one thing I guess I should address is, okay, where's this Neumann condition in the tiling? And for that, you just have to kind of convince yourself that sort of being harmonic at the boundary vertices is sort of the right discrete analog of a Neumann condition. And maybe this wasn't, sorry, and maybe this wasn't the best example because there were no boundary vertices, but in general, this is sort of the story, which is the right discrete analog of the Neumann condition is harmonicity at the boundary vertices. And so in particular, we have this idea that, okay, these tilings are the discrete analog of this conformal map. So one sort of natural way to make this heuristic precise is to prove some sort of result that you actually have convergence, right? So this is the result we would like to prove, which is, okay, you take some domain omega, I shove, right, so you take some domain omega, it has these 4 marked boundary points, and I approximate it on the inside by a graph. And since orthodiagonal maps are good approximations of continuous 2D space, they're a very natural choice for which graph I should approximate it by. Now I pick 4 marked boundary points in the primal lattice for my orthodiagonal map, and they give rise to, so we have these primal boundary arcs over here, which is basically, it's just, I take the arc between these two guys and I look at all the primal vertices along it. And similarly, we have these corresponding dual arcs, right? And this is the last primal arc. And we set up a very similar boundary value problem on our orthodiagonal map. And this gives us some similar sort of tiling. And of course, the thing we would like to show is that as we send our mesh to 0, and as we make this a better and better approximation of our continuous domain, these tiling maps, which are defined on the level of these like quadrilateral faces, these should converge to the limiting conformal map. So that's what we'd like to prove. Any comments at this point?
So just to be sure that I understand what you want to have a scaling limit of, what you'll remember from like the lattice and the tiling is just like the positions of the vertices and the rectangles, or?
Yeah, so if effectively what you've defined your map on is, okay, there's some ambiguity in that I say, okay, I send this space to this space. How I do it will turn out because I have these a priori regularity estimates. It doesn't really matter. So the gist of it is that the image, as these spaces get smaller and smaller, these sort of corresponding rectangles get smaller and smaller, and so it sort of doesn't matter. I just take some homeomorphism of this quadrilateral and I send it to the corresponding rectangle. And I do this for all the faces. And in this way, I have this, I have an honest to goodness function that sends the interior of my orthodiagonal map to this rectangle. And then, of course, as I'm filling up more and more of my domain and my mesh goes to 0, this should converge. That's the thing I'm claiming.
But so what you want, you're looking for a scaling limit for your conformal map?
I'm looking
just for, yeah, I'm not really clear on which object you're going to state our convergence result on. It's just
the tiling, right? So there's, I have my orthodiagonal map is this discrete graph thing. There's an associated tiling with it, and the point is just, well, as the mesh of this thing goes to 0 and it's a better and better approximation of this continuous thing, then this tiling map, there's no rescaling, it's just convergence.
Okay.
Yeah.
Thanks.
Cool. So It's a picture. And okay, so just some prior work on this stuff. Let me just see how I am on time quickly. Okay, sure. I'll try not to go
Yeah,
too
you
far.
have like 5 minutes, I would say.
Sure. All right. So just a very quick comment. So we have this as far as prior work. There's this stuff by there's a result by Panagiotis and Georgakopoulos where they show this convergence where your orthodiagonal map is just a finite chunk of the square grid, and omega is a Jordan domain, so its boundary is some simple closed curve. There's also this result from 2021 by Albin, Lind, and Poggi Corradini, which gives you an explicit rate of convergence in this general orthodiagonal setting, provided that your boundary consists of analytic arcs and they all meet at sort of cusps. So you have a bunch of analytic boundary arcs and there's some control about the way in which they sort of come together. And I guess one other comment is, so this isn't explicitly about these tilings, but building on previous work of Renescence Kapenkov, Jerison, Gril, Gurevich, and Nachmias, they proved that solutions to the discrete Dirichlet problem converge to solutions to the continuous Dirichlet problem. And so, you know, in particular, if these tilings are sort of very close to discrete holomorphic functions, whose real and imaginary parts we already know are discrete harmonic. And so, of course, any result about discrete harmonic functions on these OD maps is going to be, there are a lot of ideas that we use from this paper, and for fairly obvious reasons, like these are very useful. If you understand something about discrete harmonic functions, this is useful for understanding these tiling guys. And then, of course, there are these closely related tilings of cylinders, which have been studied recently by Beniamini and Schramm, Georgakopoulos, and Hutchcroft and Perez in connection with the Poisson boundary of planar graphs. So there's some work on that. Okay, so I think, yeah, just a very brief, sure, I'll make a very brief comment, which is prime ends. So prime ends on a general simply connected domain, this is sort of the right notion of what it means to have a point on the boundary. Because how did we specify our limiting conformal map? Well, we specified it by saying this boundary point gets mapped to this boundary point gets mapped to this boundary point, etc. But for general simply connected domain, weird things can happen. So in particular, you have this disk with a slit in it, and my conformal map, in some sense, it unzips this slit, and in the process, this one point over here on the boundary, it corresponds to 2 points over here. And we have a similar sort of story here, where if you have this comb domain, you can convince yourself that this line segment on this side is getting pushed to 1 point when I uniformize it and I map it to the disk. And so there's this weirdness with even talking about sort of the corresponding limiting conformal map for an arbitrary simply connected domain. And so the way we get around this is this Carathéodory compactification, right? So if you have a simply connected domain omega, you fix a reference point, and then you define this sort of metric. And then what the Carathéodory compactification of omega is, it's the completion of omega with respect to this new metric. And in particular, sort of once you do this, all your problems sort of vanish. So our prime ends are precisely the boundary of the Carathéodory compactification of omega. So in particular, in context of the picture we saw earlier, approaching the slit from the top is a different prime end from approaching the slit from the bottom, because if I have a point, say, over here, over here that's close to the top guy, and over here that's close to approaching the same point from the bottom, I need a long curve if I want to separate them, say, from some reference point in my domain, right? Okay, and then of course, okay, we also, what does it mean for G to be close to omega? So we say that an orthodiagonal rectangle, which is just this orthodiagonal map with these 4 distinguished boundary points, is a delta epsilon good interior approximation of the continuous domain if, okay, the epsilon just means your mesh is at most epsilon, and in line with this Carathéodory metric business, we say that we have this condition that, what does it mean? Right, so we have one condition which is the edges at length at most epsilon, and we have another condition which is has to do with the boundary of my discrete guy being close in Carathéodory metric to the continuous guy. So here we've written down this statement in terms of crosscuts that join AB and separate it from CD. But the only reason we reference CD is we just want to avoid having to throw in this reference point. So really the intuition to just have is that there's this Carathéodory metric, which is sort of the right metric with which to look at a general simply connected domain. And so naturally, what does it mean for our orthodiagonal map to be close? Well, one thing we want is that all of these boundary arcs should be close to the corresponding continuous boundary arc in Carathéodory metric, right? And so our main result, so this is forthcoming work with my advisor, Ilya Binder. So if you have a bounded simply connected domain, you have these 4 distinguished prime ends listed in counterclockwise order. You have a sequence of orthodiagonal rectangles that are a delta n, epsilon n good approximation of omega, where delta n and epsilon n go to 0. Then the corresponding tiling maps will converge uniformly on compacts. And I'll just say, just very briefly, so how do you prove this result? It's exactly the framework that we discussed earlier. So firstly, you notice your tiling map is close to a discrete holomorphic function, namely the one that agrees with Hn. So this is the solution to the boundary problem on the primal lattice that gave us our tiling map, and Hn tilde, which is the boundary value problem on the dual lattice, which was the second ingredient in our tiling map. And then in step 2, we show that these phi n's are uniformly bounded and equicontinuous, right? So uniform boundedness follows from some estimates on extremal length. And then equicontinuity follows by sort of adapting this argument that exists in this Jerison, Gorel-Gurevich, and Nachmias paper. So we effectively, it's not fantastic, but we get some sort of uniform modulus of continuity for these tiling maps, or for the real and imaginary part, but effectively for the tiling map. And so similar estimates already appear in the work of Alden, Lind, and Poggi-Corradini, and maybe just a comment, which is okay. We do genuinely need this estimate up to the boundary because we're interested in the boundary behavior of our guy. But in the bulk, this is actually really subpar. So in particular, once we know that our functions are uniformly bounded, using these results of Shelcock, Losley, and Ruskik, we can actually get Holder regularity for the tiling map, as long as we're away from the boundary, right? And then, of course, okay, Barzella, Ascoli, these guys are pre-compact. They converge with respect to this topology of uniform convergence on compacts. Then we show that any subsequential limit of these guys is holomorphic. Basically, if we have a bunch of discrete holomorphic functions, they converge to a holomorphic guy in the limit. And then there's this subtlety, which is, okay, usually we can identify this guy based on its boundary behavior. But in our case, these real and imaginary parts, they came from solving a discrete Dirichlet-Neumann problem and not a Dirichlet problem. And so we only have a partial understanding of the boundary behavior. But the way we get around this is you just use the argument principle with the limiting holomorphic function, along with sort of this partial understanding we have of the boundary behavior, to show that G is not only holomorphic, it's actually conformal. And being conformal plus this partial understanding of the boundary behavior, this is good enough to uniquely identify our function. And so, since any subsequential limit of our guys is the same, we know that they converge to this line over here. So I think I may have already gone over time, but so thanks for listening to that spiel. And of course, if you have any questions, particularly, I was moving very quickly through the technical details towards the end, but if you have any questions about this stuff, I'd be happy to answer it.
Oh, thank you. I don't know if anyone has questions. I have a few, but okay. So I'm still, first of all, I'm still a bit confused about like the precise sense in which you have a limit, because so your functions phi n a priori were defined on your lattice in some sense, or
oh yeah, that's a good point. Sure. So I guess the thing I'll say is at least the tiling map you'll agree is defined in the, or it's not too hard to see how it's defined in the plane, right?
So you extend it or interpolate some things to have something that's defined in the whole domain omega?
Yeah. So I mean, for the tiling map, it's kind of easy because the tiling map is defined on the level of faces. And so for it just sends this face to this face. And so we just pick some homeomorphism for each face. And in the process, we get, some map that sends this thing to this thing. And so, of course, we can talk about uniform convergence on complex because eventually this is a better and better approximation of our continuous guy and so, of course, for any fixed compact set, eventually our orthodiagonal maps will cover it and we can talk about the convergence.
I see. But yeah, they're not defined on omega, so a priori it's a bit confusing to compare the two.
It's eventually you're defined on all of omega, and that's good enough. All you care about is complex. Sure.
Okay. Yeah. Okay. So that's clear to me now. Thanks. And so another question is that, so you mentioned that at some point you have difficulties in your proof because you're not exactly solving a Dirichlet problem. And that's the thing, like that's the main difference with the article that you mentioned that works on Dirichlet, like convergence of Dirichlet solutions in the discrete to solutions in the continuum.
Yeah.
Okay.
Yeah, that's sort of, there's this, because, you would like to just like plug these results in, but it's sort of, in this case, technically, like we said, this is sort of, you have a Dirichlet-Neumann problem because if we have this boundary value problem here, right, say like for the H guy, then what happens on the primal edges that are over here, say, along the boundary? Well, you're just harmonic at this primal edges. And we sort of agreed that, okay, being harmonic at the edge without specifying any sort of boundary value, this is sort of the right discrete analog of a Neumann condition. So yeah, you have to, I guess the one sort of thing I'll just comment on is, our modulus of continuity, it's a bit of a restrictive statement in the sense that, a soft, he has this result where it's like you write down a modulus of continuity and it works for any solution to the Dirichlet problem sort of away from the, whereas here it's sort of, the way we can adapt as proof, but sort of the reason we can adapt as proof is because our boundary conditions are sort of really easy. It's like 0, 1, and then your Neumann along 2 arcs. Whereas, so it's a statement that sort of our modulus of continuity is very specific to this problem. It's not like I have a general modulus of continuity for the solution to a Dirichlet-Neumann problem on orthogonal. That I don't know how to do. Yeah.
I see.
So
but
you really
yeah,
have
you
to
still have to take into account that you really want to know what happens at the boundary, but it's still a relatively easy case, let's say.
Yeah, it's sort of like you really like there are all sorts of nice things like sort of the structure of like the level sets of this function, and this turns out to be like kind of important. Whereas like for general, I don't really know how to handle general Dirichlet-Neumann guys. I know how to handle sort of stuff that either is this or looks fairly close to this.
So do you have like in mind for future projects to try to tackle more general Dirichlet-Neumann problems or solutions?
At some point, I think so. Sort of the local things that I think are sort of interesting in this direction. I think one thing is definitely we improved on sort of the modulus of continuity estimate in this convergence results in like this paper of Alban, Lind, and Cauchy-Riemann. Sort of we improved on their sort of adaptation of the Jerison-Grigorevich like Nokmias estimate. And so it seems sort of highly plausible that, okay, we can also improve on their rate of convergence, and we can give this rate of convergence for domains that aren't just analytic. Like, I think I could probably do it for guys that are like rectifiable or something. Having rectifiable boundaries is already good enough to get a rate of convergence for these tilings. So one thing is rate of convergence. I guess if you're more interested in sort of like graphs and stuff, there's a very closely related sort of, maybe I'll just draw the picture, which is, so what I can do is, let's say I take a random triangulation. Okay, pretend this is a triangulation.
Well, there's a few, yeah, okay.
I failed miserably, but effectively,
I think if you add one edge, it would be good. Yeah, okay, well.
Oh, anyway, I don't know how to fix this, but effectively, sort of, there's a story where there's a very similar sort of uniformizing conformal map for, say, like a random triangulation where you take, let's see, what do? You set this to be, zero. You fix the value of the vertex? Yeah, right. So you fix the value here to be 0. You fix this to be something else. Okay, maybe I won't get into this, but sort of one thing that would be interesting is effectively, so these square tilings in and of themselves, they're already a way of uniformizing graphs that's sort of in some sort of way that preserves conformal structure. And there's a very similar sort of discrete conformal map if what you have is sort of a discrete annulus, roughly. I don't know. And so, whatever, this is very much not an orthodiagonal map. There's a lot of stuff missing, but okay, you have some sort of graph-like thing. It's roughly topologically an annulus, and you can map it to an honest-to-goodness annulus. Then you can do something similar for, what I can do is I can take a random triangulation or something like that, or even, you could do this with random quadrangulations, where effectively there's some similar story where I can set up a boundary value problem, and I can get, again, I get this night. Oh no, okay. Yeah, I know exactly what this is. Good. This took me a moment. So what I do is I fix a vertex here. So maybe h is equal to 0. And then maybe for the outer guy, I set h equal to 1. And then h tilde is the discrete harmonic conjugate of h. And then in a very similar way, I get a tiling of an infinite strip, right? Because now there's a sort of singularity here. And so this is a h tilde is this multi-valued function. And so I get a tiling of an infinite strip. And then, of course, it's very easy to just map this thing to an honest-to-goodness annulus. So you get some sort of picture like this. And then what you would like to say is now, okay, if you do this, say, with a random triangulation, then you get some sort of uniformization of this guy in the plane. And of course, okay, proving that these things converge to Liouville quantum gravity is like very hard. And I don't know most of that machinery. But I think there's a very similar sort of, there's a paper in this vein, again, by Nachmias, Jerison, and Grigorevich, where they show that, okay, if you take these mating of trees maps and you circle pack them, you can't show that they converge to Liouville quantum gravity. But you can at least show that, okay, the circles that I get in my uniformization, their like radius goes to 0. So you can just be less ambitious. And maybe you could say something, you have this picture, maybe you could say something similar for this picture where you say, okay, I can't show that it converges to Liouville quantum gravity. I have no idea what the limit is, but maybe I can say, okay, at least there's probably some sort of limit because these little tilings these tiles that correspond to my edges, they shrink to 0 or something like that.
And in that problem, maybe, I know there are like some natural observables that you could try and show that they converge to something related to Liouville.
I mean, this stuff is very, I don't know, this stuff is pretty, I feel like it's very hard, at least, because like, I mean, this is the thing that everyone says. Like, if you read like Nachmias's paper and Chalcock's papers, they'll say things like, the goal of this sort of discrete complex analysis program is, of course, you want to be able to handle random graphs so that you can apply these techniques to sort of embeddings of random graphs. But then, as far as like being able to actually do this is sort of, it's very much above my pay grade at the moment. I think, I mean, sort of the first sort of rigorous results to this effect, they were, like I said, it's this paper of like Holden and Son, which is very recent, and it was published in ACTA. So this is very impressive stuff, but it's also hard.
But I guess maybe in like a decade or so, there
might
be something related to rectangle tilings of cylinders.
In a decade, like this is something they'll be just like teaching like in a standard graduate course or something. I don't know.
It's never a bad thing to have a bit of ambition for future projects.
Any other questions and stuff?
Let me check in the chat. It doesn't seem so. Well, if no one else has questions, then we can thank David again for this very nice talk. And yeah, we can clap again if you want.
Why not? Thank you very much for this talk.